Good morning, guys. Today we're going to be doing our lesson a little bit different, given the circumstances and everything going on. I hope everybody is safe at home and is safe during this time of crisis, and that you're with your family. Stay safe, take precautions, and and I hope everyone is just safely in their homes. And today we're going to be talking about solving exponential equations that have like bases. Okay, and today what we're going to look at is, what do we do if we have exponents that have the same base, and we're going to be solving equations with those exponents. And so, to start off the notes, right, we have exponential equations are equations in which variables occur as exponents. To solve these equations, we must use the following property: the property of equality for exponential equations. And so I have an example here. If I have an equality between two exponents with the same base, whatever that base may be, whatever number it may be, then we can make the assumption that the exponents are equal as well. So the example here is, if I have two exponents that have the same base, the base of 3, then what can we say about the exponentials? They should be equal to each other. Okay. And so I'm also going to show you guys some of the steps that we want to look at when we're solving equations like this. Okay. So step 1, what we want to do is we want to determine if the bases on both sides of the equation can be written with the same base. Step 2, we want to rewrite the problem using the same base for both sides of the equation if necessary. Step number 3, use the properties of exponents, which we saw, I think 2 tests ago when we did a test on exponents. We're going to use those properties to simplify the problem if necessary. Okay. Step number 4, apply the property of equality for exponential equations. So one thing I want to say about that is this property of equality that is mentioned here is the same property, let me zoom out a little bit, is the same property that we see up here. Okay, so this step number 4 is applying the property that we see in the part that I boxed above. Okay, so let me continue on the steps here. Step number 5, solve the problem by isolating the variable. And I just want to reiterate there that when I isolate the variable, that means make sure the variable is by itself. Isolating the variable, making sure that the variable is by itself. All right, so let's look at the first example. Oh, and as you're working on these, feel free to work them out on your own sheet of paper. I know some of you may have a printer at home, you may not have a printer at home. But I think the easiest thing is, just to get blank paper, something to write with, and just on your own sheet of paper, just follow my steps. Write down the problem, copy it, do it on the side as you're watching the video, and just follow my steps. All right, so let's look at example 1. So, example 1, remember, step 1, let me zoom out a little bit so we can see step 1. Step 1, determine if the bases on both sides of the equation can be written with the same base. Okay? So in other words, do these two sides of the equations, do both sides have the same base? Yes, so then we can skip step 2 and even step 3 because it's pretty straightforward. It's pretty straightforward. What we're going to say is because these bases that I'm circling here are the same, then we can make the conclusion that these exponents are the same. So I can make the conclusion that 2x equals 10. Now, solve by isolating the variable. It's step 5. So how do you get rid of the 2? What's the opposite of multiplication? Division, right? So we divide 2 on both sides. X equals 5. First one. All right. Let's go to the next one. Okay. Example 2. Step 1. Check to see if both sides of the equation have the same base. And I noticed that, on the right side, it's not written in base form. I don't see a base of 3 on the right side. So step number 2 says rewrite the number into an exponent. So what that means is, can I think of a power of 3? Let me zoom in here. Can I think of a power of 3 that will give me 81? So let me write that out here on the side. So my question is 3 to what power equals 81? Give you some time to think about that. 3 to what power gives me 81? And it's actually 3 to the power of 4. That's 3 times 3 times 3 times 3. So what I'm going to do is rewrite the equation. So I'm going to copy the left side equals, and instead of writing 81, I'm going to write 3 to the power of 4. And now, because the bases are the same, they're both base 3, then what can I say about the exponents? They must be equal. And so now we move on to step 5, where we isolate the variable. So how do you get rid of the 4? Right? The opposite of multiplication is dividing, so we're going to divide both sides by the 4. And so x equals 1. X equals 1. And if you're still copying and writing stuff down, feel free to pause the video wherever you want to pause it, wherever you see that you can pause and kind of copy down or write down the steps that we did. All right, let's go to step 3. Example 3. All right. So again, we want to ask ourselves, do both sides of the equations have the same base? And we want to think about, from the rules of exponents, 2 tests ago, what do we say about negative exponents? What do we say about negative exponents? And if you remember, what we want to say here is that 2 to the negative 1, to make the exponent positive, we move the 2 to the bottom. We move the 2 to the bottom, and the negative 1 becomes a positive 1. So instead of writing 2 to the 1, I'm just going to write it as 2. So I have a substitution here. I can say that this can be rewritten as this. So if I make that substitution, let me box this out so it's not confusing, but this is kind of a rule from the last test. But now in my next step, I can write 2 to the negative 1 equals, then I'm going to copy the right side. So the left side changed to 2 to the negative 1, and I just copied the right side. And now that the bases are the same, they both have a base of 2, then I can say that the exponents are the same. Gives me the following expression. And then I want to isolate the variable. So the opposite of subtracting 5 is adding 5 on both sides. And so I get x equals 4. X equals 4. Okay. Awesome. Let's go on to the next example. Example 4. Now kind of using the same idea, similar idea as example 3 that we just did. Can we think of another way of writing 1 over 25 so that there's some sort of base of 5? And the reason I want to look for the base of 5, or I know I'm looking for that, is because the left side has a base of 5. Okay, the left side has a base of 5. So, give you guys some time to think about it. And so what we should come up with is, if I have 1 over 25, that's the same thing as 1 over 5 squared. But if I want to move the 5 squared to the top, I can move the 5 to the top, but then the 2 becomes negative. And so I can say that I can replace 1 over 25 with 5 to the power of negative 2. So I'm going to copy the left side, and then I'm going to rewrite 1 over 25 as 5 to the negative 2, and then copy the negative 8 on the outside. All right, and then we come up to a situation from the exponential exponential properties, right? We call this the power rule. I have an exponent raised to another exponent, so that means that these two exponents can multiply, and a negative times a negative is a positive. I'm just going to copy the left side, and then I'm going to multiply the exponents. So negative 2 times negative 8 is positive 16 as an exponent. And so now that the bases are the same, I can say that the exponentials are the same. So I can say that 2x equals 16. The opposite of multiplying is dividing, so I divide by 2. And so x equals 8. Right. Let's move on to example 5. Now, this is, I guess you could say it's kind of like a trick question, but what we notice is that one side usually has a base of interest. In this case, the base is 6. And we want to make sure that both sides of the equations have the same base. So my question to you is, if I want to make sure that the left side has a base of 6, so I have the base of 6. And the question is 6 to what power, question mark here, 6 to what power equals 1? So I can make a substitution. 6 to what power equals 1? And what should come to mind is 6 to the power of 0, because anything to the power of 0 is 1. So that means I can make a substitution actually, I should have done the arrow the other way, right? I've been doing the arrow the wrong way. But I can make a substitution and replace 1 with 6 to the power of 0. So I'm going to rewrite 6 to the power of 0, copy the right side, and now look what we have. We have that both sides have the base of 6. That means that the exponents are equal. So that means I have 0 equals 4x minus 6. The opposite of subtracting 6 is adding 6. So just solving like algebra. 0 plus 6 is 6. Bring down to 4x. These cancel here. The opposite of multiplying by 4 is dividing by 4. And so I get x equals 6 over 4. But can we reduce 6 over 4? Yes, right? They're both divisible by 2. So 6 divided by 2 is 3. And 4 divided by 2 is 2. So my final answer is 3 over 2. Let's move on to the next example. I hope you guys are kind of getting the idea. All right, next one. Okay, so here I see that, 25 and 125. Is there some way to write these bases, the base of 25 and the base of 125? Do they have a common base? What I mean by that is, what should come to mind, or what you should think of is 25 is equal to 5 squared, isn't it? 5 times 5 is 25. Okay, and then 125 is actually equal to 5 to the third power. 5 times 5 times 5, right? If I multiply 5 3 times, I should get 125. So I'm going to make two substitutions here. I'm going to substitute 5 squared for 25. And I'm going to substitute 5 to the third for 125. So I'm going to make two substitutions. So I'm going to make my substitutions in this next step. So I'm going to put 5 squared, right, instead of 25. 5 squared. Then copy the x minus 1. And then 125 becomes 5 to the third. Copy 3x plus 4. Okay. Now this next part that we're going to do, and let me pick a different color here. The next thing we're going to do is we're going to make sure that we use the power rule correctly. So think of this as having a parentheses and a parentheses here. And so we're going to multiply 2 times x and 2 times negative 1. Then on the right side, we're going to multiply 3 times 3x and 3 times 4. So what is, on the left side, what is 2 times x? 2 times x. That's 2x, right? So what we're going to end up with is 5 to the power of 2x minus, what's 1 times 2? That's 2. Equals 5 What's 3 times 3? That's 9x plus 3 times 4 is 12. So we end up with both sides of the equation have a base of 5. So that means that these exponentials are equal to each other. So I can write 2x minus 2 equals 9x plus 12. And then let's solve. So I'm going to subtract 2x on both sides. Bring down the negative 2. 9 minus 2 is 7. Bring down the 12. Then subtract 12. And let me move this up a little bit. Okay, subtract 12. And negative 2 minus 12 is negative 14 equals 7x. And divide both sides by 7. And so my conclusion is x equals, what's negative 14 divided by 7? It's negative 2. So I ran out of space there, but that's the solution, right? So negative 14 divided by 7 is negative 2. So let me zoom out so you could see it and maybe pause it there if you want. Okay, example 7. Example 7. Okay, so what we can do here, we have something different here. And what I like to do is I always like to make sure that I can, move the denominator. If ever I have a fraction, I want to ask myself, can I move the denominator? In other words, is there a way that I can get rid of the denominator and there is a way. And what I want to do is I'm going to copy it because I feel like there's not enough space here. So I'm going to copy the problem exactly how it is. And I want to say that to get rid of the 81, right, what's the opposite of dividing? Actually, sorry for this. I'm going to leave more space on the left side. Okay. So rewrite it here. Right. So the opposite of dividing by 81 is multiplying by 81. So I'm going to multiply 81 on both sides so that these 81s cancel. And I'm left with 3 to the 4x equals 81. And then you should think that this is familiar to something, but you should say, I know that 81 is 3 to the power of 4. So I'm going to replace 3 to the power of 4 with 81. So I'm going to end up with 3 to the 4x. Just copy the left side, equals 3 to the power of 4. The bases are the same, so that means the exponents are the same. And so I have 4x equals 4. Divide both sides by 4, and that means that x equals 1. Okay. Let's move on to example 8. All right. For 8, if you notice on the right side, there's a multiplication going on here. And what did we say when we were talking about the rules of exponents? What did we say about exponents with the same base if they are multiplying, what happens to their exponents? Right, so I'm going to copy the 36, and what we should think of is that what happens to the exponents is that they add. So it's going to be 4x minus 6 plus 3. Copy the 36, and so I'm going to get 4x. Negative 6 plus 3 is negative 3. And then we should also think of, 36 is actually 6 to the second power. It's kind of a side note here. And so I can make this substitution and say 36 is actually 6 to the second power. Copy the right side. And what do you know? We have the same base. So if we have the same base, what can we say about the exponent? That the exponents are equal. And then we just solve. So opposite of subtracting 3 is adding 3. 2 plus 3 is 5. The opposite of multiplying by 4 is dividing by 4. These will cancel. And so my answer is x equals 5 over 4, right? Nothing to simplify. There's no fraction to simplify. It's already simplified. So that's my answer, 5 over 4. Let's move on to example 9. All right, example 9. It looks like example 7. Remember we had the fraction in example 7? And what we can do here is we can say, the opposite of dividing by 8 to the power of x is multiplying both sides by 8 to the power of x. So that this cancels with this, the left side, right? 8 to the x cancels with 8 to the x. So I'm left with 2 to the power of x plus 3 equals, now do these two, right, they're going to multiply, but do they have the same base? Do they both have a base of 8? Yes, right? And again, using the rule of exponents, this is the product rule. If I'm multiplying two exponents with the same base, their exponents actually add. Their exponentials add. So it's going to be 8 to the power of 3x minus 10 plus x. So where did this x come from, right? It came from this one. So it's 3x minus 10 plus x. And what I'm going to do is on the right side, I'm going to combine like terms because I want to say, what's 3x plus x? That's 4x minus 10. Now, what should come to mind is, can I write 8 as a base of 2? Is there a way to write 8 as a base of 2? And what should come to mind is that 8 is equal to 2 to the power of 3. So again, this is kind of a side thought. And so I can make a substitution here, replace it. Right, so it's going to be copy the left side, and I'm going to replace 8 with 2 to the power of 3, and then I'm going to copy 4x minus 10. And what we're going to do is, like I did a little while ago, I forgot what example it was, but we are going to make sure that we distribute the 3, so we're going to multiply 3 times 4 and 3 times 10. So I'm going to copy the left side again. So it's going to be 2. 3 times 4 is 12 x, don't forget to bring over the x, minus, what's 3 times 10? 30. And then we should say, oh, I have same bases on both sides. We have like bases. And so that means that the exponents are equal. And so I have x plus 3 equals 12x minus 30. And I'm going to subtract x. The x's will cancel on the left, and I'm going to be left with 3 equals 11x minus 30. Uh-oh, it looks like I'm running out of space. The next thing, right, what's the opposite of subtracting 30? Adding 30. So I'm going to add 30 to both sides here. These will cancel. And 3 plus 30 is 33. And so, right, what is 33 divided by 11? X equals 3. I hope you can see that. Okay, x equals 3. Right, 3 times 11 is 33. Okay. All right, one more example, and we'll be done for today. So let's do that. Let's move over to the last example. And this last example is one of those combination ones where we graph on one side and we solve on the other side. Okay. So let's read. What does it say? Exponential equations and exponential functions. Remember, solutions to an exponential equations are the zeros of the related exponential function. And what are zeros again? To remind us, the zeros are the x-intercepts of the graph. So the solutions that we're going to get over here are answer, like what we've been getting in our examples, right? We've been getting an answer for x. This answer that we get is going to represent or equal the x-intercept that we get when we graph this. Now, one thing we have to connect is from the last lesson we were talking about logs, and what we have to remember is that the exponential function and the log function are inverses of each other. So on the left side we're going to graph this function, and on the right side we're going to find the zero. On the left side we're going to graph this function and find the zero, the x-intercept. Then on the right side we're going to solve this equation. Alright, so let's graph first. I'm going to zoom in here so we have a big view here. And what we want to look at is, when we're graphing an exponential, if you remember about logs, logs had vertical asymptotes, right? These vertical boundaries. But exponentials actually have horizontal boundaries. Okay? And if we notice here in the exponential, there's a couple of transformations going on. There is a negative in front. So I'm just going to circle this negative. And the negative means reflection over the x-axis. Okay. Then we have x minus 3. X minus 3, that means we're going to move to the right 3 spaces. And then the plus 4 means we're going to move up. So I'm kind of color coding things here. And so one thing I want to mention here is, if we're moving up or down, this part that tells us if we're moving up or down is going to determine the asymptote. It's going to determine the asymptote. So how many units are we moving up? We're moving 4 units up. So that means that our asymptote is y equals positive 4. Y equals 4. What's the base of this function? It's 2 right here. So the base is 2. Right. And now that we know the base of the function, if you guys remember from transformations of functions, we talked about the parent function. And so, and let me put a blank, 5 values of x. And I'm going to pick these specific ones, and we're going to keep using these same x values. But then my question is, what would be the corresponding y values? So remember, we're going to be using these, -1, 0, 1, 2, 3. So those are my x's. So my first number is 1/2. My second number was 1, 2, 4, 8. And remember how we got those, right? 2 to the power 0 is 1, 2 to the power 1 is 2, 2 squared is 4, 2 to the third is 8. Okay. So what transformations are happening here? There's movement to the right. Now, movement to the right is affecting the x's or the y's? That's right, it's affecting the x's. So if we're moving to the right, are we adding 3 or are we subtracting 3? That's right, we're adding 3. So what's going to end up happening is we're going to be adding 3 to all these x values. Okay. What's going to happen to the y values? Well, the reflection over the x-axis is going to affect the y values, and moving up also affects the y values. So the reflection means I'm going to multiply all my y values. All my y values are going to be multiplied by -1. Then I'm going to, after I multiply by -1, I'm going to add 4. Because we're moving everything up 4. Okay, so that's going to give me a new table. Or a new table of values. So it's going to be x and y. So let's add. What's -1 plus 3? -1 plus 3, that's 2. What's 0 plus 3? That's 3. What's 1 plus 3? 4. What's 2 plus 3? 5. What's 3 plus 3? 6. So those are all my new x values. My y values. I'm going to do 2 steps. I'm going to do the operation or transformation in red and in the purple one. So first one, what is -1 times 1/2? That's -1/2. And then what's -1/2 plus 4? -1/2 plus 4. What is that? That would be, that's correct, 3.5. Next one, what's -1 times 1? -1. What's -1 plus 4? 3. Next one, what's -1 times 2? -2. What's -2 plus 4? 2. And I hope you're getting the pattern here. What's -1 times 4? It's -4. What's -4 plus 4? 0. 0, right? One more. What's negative 1 times 8? Negative 1 times 8 is negative 8. What's negative 8 plus 4? Negative 4. Okay, so those are my new values. And that's what I'm going to plot over here. So first point is 2 and 3.5. 2 and 3.5. So that would be 2 and 3.5 would be about here. The next one is 3, 3. Be here. The next one is 4, 2. Be right here. The next one is 5, 0. And the last one is 6, negative 4. And remember, we said something a little earlier. On the top here, we said there's an asymptote. Remember, these are boundaries. And we said that exponentials have a horizontal boundary. Exponentials have a horizontal boundary. So this y equals 4 is going to be a horizontal boundary. So I'm going to draw a horizontal boundary here in orange. It's going to be my my asymptote there. And then I'm going to connect the dots. But for an exponential, it's going to look something like this. Let's see if I can finish it here. If I can finish it. There we go. There we go. That's my exponential graph. What's the domain? What's the range? And what's the x-intercept? Domain. If I'm going from left to right, this arrow is going towards negative infinity. Then this arrow is going towards the right, towards positive infinity. The range, going from the bottom to the top. If I'm scanning from the bottom, this arrow is going down towards negative infinity. And it's going up, but does it go past this boundary? No, right? Where's this boundary at? The boundary is at 4. So my range stops at 4. Parentheses. 0. Where is the 0? Remember, the 0 is the x-intercept. So where did this blue graph intersect the x-axis? It intersected it at 5. So x equals 5. Okay. So now let's work on the right side. And at the end, we should compare and see that the right side gives us the same result as the left side. Okay. So one thing, as we work out this right side, what we can do is we can move the 4 to the other side, right? So the opposite of adding 4 is subtracting 4. Actually, let me write it a little bit bigger here. I'm just going to copy the problem again, just so it's a little bit bigger. So I copied it. So the opposite of adding 4 is subtracting 4. So we bring down the negative 2 to the power of x minus 3. Then we see that these will cancel. And what's 0 minus 4? Negative 4. And how do I get rid of a negative? Can I divide both sides by negative 1? Yeah, then I make both sides, because I'm dividing by negative, both sides become positive. And then we should think of, isn't isn't 4 2 squared? So can I replace this with 4? Yeah. 4 becomes 2 to the second power. We have the same base, so that means that these exponents are the same. And so that means that x minus 3 equals 2. Then solving for x, we add 3 on both sides, and x equals 5. What do you know? Is it the same? Yeah, my solution was x equals 5. So what we should see here is that these two are the same. So what I'm going to do here is I'm going to zoom out. That way, if you guys want to pause, you can have it paused on the screen that shows all the examples worked out. But thank you for joining me today. And I hope that, again, like I said, I hope that you're safe and you're well. And I'll see you when we get back. And thank you for joining me. And I hope that you have an awesome rest of your day. Thank you. Page here, but if I have a parent function that looks like this, y equals 2 to the power of x, we're looking at what transformations are happening to this function, right? And so what I'm going to do is on the table, I'm going to pick. Now my y values, I can find them by substituting the different x's that I chose right now, which is this one, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3 is going to give me 5 y values. And we should say, 2 to the power of negative 1 is 1 over 2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared, 2 times 2, right, is 4. And 2 to the third is 8. So those are going to be my y values. So I'm going to put these in my table. I'm going to copy these numbers into my table.